Hello, I'm Lyndon Smith. I'm the Professor in Computer Simulation and Machine Vision at UWE, and I'd like to give you a little talk today about robot vision. That's my email address, by the way, if anybody wants to contact me. But let's talk about robot vision for a start. What is robot vision? Well, I would say it's machine vision that's powerful enough to allow tasks to be undertaken robotically. And we can achieve this by gathering richer data, that's to say 3D as well as 2D data, and learning from experience. And then we exploit recent developments, as it says there, in 3D vision, like the Azure Kinect camera, which is a very powerful RGB-D camera, D for distance, it gives you range data, and AI, deep learning, convolutional neural networks, for example. So, talking a little bit more about the kind of things we've done in our lab and the impact we've had would really involve describing things like Cubiscan, Petroscope. These are different solutions we've had for industrial problems in different sectors, and we provided systems to clients all around the world, in fact, over the last 20 odd years. HarvestEye, that's commercially, a lot of these systems are now commercially available and are providing advanced functionality, like in the case of HarvestEye, measuring the size of potatoes on a harvester in the field. Non-contact wheel alignment in India, I'll talk a bit about that later on. New companies set up, account condition lameness monitoring, 3D potato metrology, skin texture analysis for the skin analyzer, which I'll talk about. We got 12 patent applications so far. So what is machine vision then, since I just mentioned machine vision? Well, we have a system where we capture an image using commercial equipment, which is not that expensive, off the shelf, arranged in innovative ways. And that could be 2D, 3D cameras, or even thermal or multispectral. And then we process the images and do analysis to get understanding from the scenes. Here we've got a non-contact vision system for measuring breathing that we developed from the NHIR grant. This is our pig recognition system that we developed. And this is a system we developed, 3D face recognition system we developed for the London Underground, which is now functioning in central London. You can see that in a lab in Farringdon. So the whole range, that's just some examples, a whole range of applications. And a lot of the time we're talking about, as I say, about 3D data acquisition. And this is realised through a technique that we have been developing for the last 20 years called photometric stereo. Now this involves one camera and a set of lights. The lights are in known positions, and we call that structured light. We turn one light on at a time and take an image each time. So if we had 4 cameras, we get 4 images. You can see they're illuminated from different angles here. Then we apply what we call a lighting model to get 3D and 2D data from the scene. So the actual 3D data we get is something called a bump map. So it's a dense array of surface normals. Each of these little arrows is the normal to the surface at that point. And then you can visualize this, what we call a rendering, and it's like a 3-dimensional model without any color, basically. So we're getting 3-dimensional information. This is the system we use for the London Underground. It can't be spoofed, face recognition that uses this technology. It can't be spoofed by holding a photograph of somebody else in front of your face, which most systems that exist at the moment can be. And we've used photometric stereo in a very wide range of applications, actually. I just go, for example, to camouflage removal. We did a project for the MOD. So this is a mask we made up, 3-dimensional mask we made up with colours. And then we had a camera and 4 lights and we captured these images. Then we applied our photometric stereo analysis and we got the surface gradients. That's a 3D surface. And so what we can do then is separate what we call the depth map, the distance from the camera, from the albedo. The albedo is just the colour. It's a bit like a normal image you take of reflectivity. And the project we did for the MOD involved us going over and getting some equipment actually from Toys R Us. We got these little toy guns and hand grenades. And we put them onto a surface and did some pretty good camouflage. You can see it's not very obvious what we got there. Then we apply our technique, and you can see very clearly the 3D profile of what we have there is very clear. The camouflage is removed. It can be removed very easily. It was quite a successful project for the MOD. They were quite pleased with that. Thought we could use it on different scales. You could use it on a large scale in the field, or just up close, because it gives you this three-dimensional information, which is quite useful. You could detect suspicious items under clothing, like explosives and so on, actually using this technique. So what I'd like to do now is go through a few case studies of things that we've done in our lab and useful functionality we've produced. The first thing we did was for a company called Quantronics in Salt Lake City, and we developed this large-scale metrology system for measuring air freight on pallets up to 6 feet by 6 feet by 8 feet, so a pretty big scale. And we made it for them, and they sold it back to the UK actually, and they told us they sold over £1 million worth last time I spoke to them, $1 million worth, sorry. And so it's easy to operate. There's obviously nothing to crash into. It's all ceiling mounted there. And we got it working. It even works in quite bright lighting actually. So that gave us the funding doing that project to set up our machine vision lab, which we've been developing over the last 20 odd years. But that was our first important project. Other examples of projects we've done over the years include an aggregate analysis project called the Petroscope we did for a company in Iceland, and he had nothing when he came to us, this chap, but we developed this for him, and he started selling the system. So the idea is you do analysis of aggregate as it's being produced in the quarry rather than sending it off and waiting for 2 weeks, and in that way you can make sure you got what you need, and you can stop the mining if you haven't got the right kind of stone, which is obviously better for the environment than carrying on digging it out when you can't really use it. So that's a Petroscope. Then just showing a wide range of sort of applications of the things we did. We had a project. A student said to me his father was running a company, a student in one of my master's courses. I said, oh yeah. And then it turns out he did. And we developed the system for him for like £100,000. He paid us. You can see that these pillars here contain cameras and lighting, lasers, and we are accurately able to produce a system that accurately measures wheel alignment and completely non-contact. So normally you hang things on the wheels to do this, but with this system it's completely non-contact, and we, after a lot of effort and work, we did get it working very accurately, and he's now selling this in India. Then we had the photometric stereo system, which we called PhotoFace, and this is the rig here. You can see these infrared lighting here in a high-speed camera. So this applies photometric stereo as you walk through it. It was designed for airports, and you can see the kind of resolution we could get from the skin. You can't really get this with other 3D cameras, really. They don't generally give you this kind of resolution. And then we applied also photometric stereo to the palm, and the idea here is to combine wrinkles and skin textures into a new type of biometric for the palm. And we got a very nice paper which I got accepted at a conference in San Diego later this year. Will be presented on this hand scanner system. Good for the COVID situation because obviously non-contact. You just hold your hand above the camera or below the camera, depending on how it's configured, and then it will grab this information at high resolution without any contact with your palm. It's better than the finger readers that you get on the entrance to sort of gyms and so on at the moment, really. Then a project which is very close to my heart is, of course, the UWE Skin Analyzer, where again we got photometric stereo with 6 lights and a central camera, and we can recover fairly high quality, high resolution images of the skin, and we can separate the 2D from the 3D, and also do quite good teledermatology, because we can do interactive visualizations of the skin where we can move the virtual light around and we can move the viewing position around. So rather than we're with the patient. So it could be useful in Australia, say, where the doctor's in Sydney and the patient's in the outback, and then you can't travel, say, 1,000 miles very easily, but this could do it for you. And also we can measure the ABCD characteristics, which are 2D characteristics of moles, and we can measure it repeatedly, and therefore we could detect change, which is a very good indicator of suspicious moles. At the moment it's very difficult for doctors to detect change in moles, and therefore difficult for them to be reliably sending people to the specialist clinic. And here is an example of what we can do with it. So we gather the albedo, which is like a reflectivity of the mole, like a 2D, the pigment, 2D picture of the pigment. And then we get the 3D textures, and then we can combine them to get the 2D and 3D, and this is where we can do the virtual visualization. And this could take teledermatology to a new level, because it's much more realistic than just the sort of webcam images we get at the moment from moles that doctors are trying to appraise. So it's two areas: automated ABCD, well, it's three areas I suppose, automated ABCD, looking at 3D textures as indicators, and then doing this virtual visualizations for teledermatology. Now, just to show the wide range of applications that we've had in our lab, I'm going from skin cancer with the skin analyzer to looking at cows. This is a favourite project of mine, this one, because I'm surrounded by farms here, and it's nice to have, and actually the farm we did this with is not far from here at my house here in Somerset, so it was nice to have a client nearby. And you can see here that we have a ceiling mounted camera which is measuring the 3D characteristics of the cow in terms of range data. And at the curvature, you can see that curvature of that spine, that is actually related to whether the cow is lame or not. And so this is a new system, can measure all the condition of the cow, give it a condition score more objectively, and also can detect lameness and thereby avoid the need for culling the cow if it's not put right, whatever's wrong with it. So it's quite a nice system. This is now commercially available, is working all around the UK. Arla are using this with their herds, actually, the UK. So let's talk a little bit of some of the applications. You might ask, what are neural networks? Because I talk a bit about neural networks. Well, what they are, as they're really a statistical modelling approach, but they're inspired by biological neural networks such as a brain. But in this case, the model is stored in the weights that connect the neurons. And we have hidden layers, and we can model complicated relationships with these networks. And really, it became very successful after someone invented the idea of backpropagation, and this is a way of training the network. So you put in your inputs and you have your outputs, you look at the error, and then you go backward through the network to alter these weights to minimize the error. That's why it's called backpropagation. So it's very powerful because it doesn't rely on any ideas of relationships. You don't assume it's a quadratic relationship or an exponential or anything like that. But it's just purely data driven, and we find it to be very powerful. And then the thing that makes even more powerful for us is when we have convolutional neural networks, which is a bit of a more complicated concept, and I can't go into it in detail here. But basically, in this, some of the layers apply convolution, which is an image processing approach, which is like in filtering, like you have in image processing software. And this uses these filters to characterize the image and detect features automatically. So as it says here, CNNs use convolution and require less pre-processing compared to other image classification algorithms. This independence from prior knowledge and human effort in feature design is a major advantage. In other words, we don't have to decide somehow what the features are we're looking for. The system does that for us. It automatically identifies the features of interest in images. And it's very powerful once it's done that. It can identify things even in the presence of changing light levels or changing perspectives and angles, and it still detects objects of interest. It does, you could argue, what maybe many people thought neural networks years ago were capable of doing. You know, you can detect pencils even if you've got lots of different images of pencils with different orientations, for example. So it's a very powerful technique that we use a lot. And one example of that is the pig face recognition that Mark's been undertaking using convolutional neural networks, and we're getting better accuracy in terms of recognizing these pigs than alternative approaches. And we've replicated the results with over 40 pigs. We trained the neural network on the pig faces, so all these pigs look the same to us, but to a neural network, you can identify the difference. So we're identifying pigs without the need for the RFID tags in the ears, which are expensive and also harmful to the pig, really, and can interfere with other radio frequency equipment on the farm. So it's a good way to identify the pig. This next picture shows how the different regions on the face of the pig were scanned, how frequently they're scanned. So the redder is the more commonly it's used by the CNN. So you can see here there's certain parts of the image of the pig are actually more important for modelling the what pig it is than other parts. We call that a heat map, an area of interest to the CNN. And also make sure that we're not modelling something else, like whether there's something in the background when you've got a certain pig appearing and things like that. Another area we've worked in is plant analysis, and we had Gitis, a student of ours, doing a good PhD in this. So again, he's been using CNNs, a thing called a mask rCNN, to segment the leaves of a plant as it grows. This is quite interesting because the leaves move around. You want to make sure that you're identifying them correctly, and he was able to do this quite well with his mask rCNN. And another application which is close to my heart is weed detection in grass. So we've got low-cost cameras, image analysis software. We're looking at commercial spraying. The CNN, after we train it with certain images of grass with certain weeds in it, can automatically identify and segment the weed. As you can see here, the red is a segmented weed. So then we can spray a bit of weed killer at the weed rather than spraying it everywhere. So we can save between 50 and 95% of herbicide, which is obviously great benefits to the environment, as well as saving a lot of money for the farmer. So this is something you're going to see a lot more of in the future. And we have successful projects working with a company, a farmer in Scotland actually. So what we're talking about here then is robot vision that can use 2D or 3D data. And often both actually. So what we can do when we have this data is we can measure the dimensions of objects accurately in well-constrained and calibrated environments. We can also segment features of interest in the image. So for example, if we have a 3D camera, we can use the range data to identify things in the foreground which are of interest in the presence of things in the background which we're trying to get rid of. Then we apply machine learning for pattern recognition as opposed to simply doing metrology. So in the example of the skin analyzer I mentioned, there we can do metrology of the image of the mole to measure automatically the ABCD rules. A is asymmetry, B is border irregularity, C is color variation, and D is diameter. So we can do that, and we can do that now, that's not a problem. The machine learning comes in when we start doing slightly more complicated things like analysis of textures. In the case of the skin, we might be analysing the texture of the skin in 3D, and we did do that, and we found that the more irregularity there was in the texture of the skin, the more chance it was of actually being cancer. So that was interesting. We could do more work, especially with deep learning, to identify other features, other indicators of moles which may indicate the presence of cancer or the tendency for cancer to appear. So having mentioned deep learning, what that provides, as it says here, is previously unseen robustness in real-world environments. And that is really useful because a lot of the time what's been really limiting many machine vision applications and robot vision applications has been variations in the environment. So you go outside and all the light's changing and shadows are being cast, and this causes tremendous problems a lot of the time for conventional vision systems. But in the case of deep learning, you need quite a lot of data to train it, but once you've done that, it's more robust in the presence of these kind of variations. And if we can make it more robust and use vision systems and robot vision outdoors, then this opens up all sorts of exciting opportunities. For example, we can develop robot systems that can interpret their environment and thereby undertake difficult tasks, maybe even in conjunction with human operators. But the robots might be able to do the more difficult, dangerous or dirty jobs in, say, a farm situation or mining or any other difficult application. And this is something that hasn't been possible up to now, but when we get this more rich data combined with this greater image understanding and scene understanding from deep learning, then we're facilitating a much more useful generation of robot vision systems. So that's really where we're coming from in the Centre for Machine Vision at UWE in the BRL. If you have any questions, you can always drop me an email. I'll get straight back to you. We're always interested in research collaborations, and we deal with companies all the time. We work with companies, as I say, all around the world, but we have many projects going on in the UK at the moment. And I'd be very happy to talk to you. This is just an example. All I've given you here is just a sort of a flash view of some of the things we've done. I have many projects I haven't covered, and there's new emerging areas all the time. But one thing I would say is that most of the time, the really exciting advanced technology is coming from the conjunction and combination of 3D data along with 2D and deep learning. So I hope that was of interest. And as I say, if you've got any questions or you've got any applications or you think you might have an area we could explore, please do drop me an email. Thanks very much.